Hello and welcome to this FP1 exam paper walkthrough. This was the January 2024 paper. You were allowed a calculator and the formula booklet. Jumping into question number 1. Given matrix M, where k is a constant, show that M is non-singular for all real values of k. Okay, for a singular matrix, we have the determinant is equal to 0, because if you remember, the inverse is equal to 1 over the determinant times by dA minus B minus C. And you can see if the determinant is 0, then you're trying to divide by 0. It doesn't work. It means it's singular, but we want non-singular. So what we're saying here is that the determinant of M cannot equal 0. So to do that, we're going to set it equal to 0 and show that there are no real solutions. The determinant of M is, if this is A, B, C, D, A times D, so that's 2k plus 1 times k plus 4 minus B times C, k times k plus 7. So that equals 2k squared plus 8, 9k plus 4 minus k squared minus 7k. That gives us k squared plus 2k plus 4. And if we set that equal to 0, you can see that delta here, b squared minus 4ac, is equal to 2 squared minus 4 times 1 times 4. 4 minus 16 is minus 12. You can't square root minus 12 with a real value. That's less than 0, therefore no real roots. Which means determinant of M cannot equal 0, which means it is non-singular. For all k, for all real k. Part B, that was part A. Part B, determine the inverse of M in terms of k. So I'm just going to apply this here. We found the determinant, so we know that M minus 1 is equal to 1 over the determinant, which was k squared plus 2k plus 4 times the matrix D, k plus 4 minus b, so that's minus k, minus c is minus k minus 7, and then a, 2k plus 1. Like so. That looks okay. So that's the inverse of M. On to question number 2. Here we've been given a function of z where p and q are integers. The complex number 5 minus 4i is a root of the equation that equals 0. Write down another complex root of this equation. Straight away we know that the complex conjugate must be a root. So 5 plus 4i is also a root of that equation. Part B, solve the equation completely. To do this, I'm going to use the fact that we know two roots already. So z minus root 1, which is 5 minus 4i, is one bracket. Z minus root 2, 5 plus 4i, is another bracket. And then if I write z minus a, where a is our third root, has to equal 0. That's what I would usually do, but I have to be very careful here because this is 2z cubed. So actually, I'm going to make this a 2z minus a to get that 2z cubed in there. What we're trying to do here then is find out what is a. To do that, we're going to expand these two brackets that we know. So I've got z times z, and then I've got minus z lots of 5 minus 4i. If I leave these in brackets for now, I might expand them in a moment. And minus z lots of 5 plus 4i. And then plus 5 minus 4i times 5 plus 4i. So to avoid silly mistakes, I'll do that up here. 5 plus 4i gives me 25. Minus 20i plus 20i disappears. And then minus 16i squared becomes plus 16. Gives me a 41. And that's just these two brackets multiplied. We still have 2z minus a here. and it still has to equal 0. Now I don't have to do any more than that, because I can see everything in those brackets in the middle there are going to be multiplied by a z. And to find out what is a, all I really need to consider is this minus 41 on the end here, because at the moment the only constant term coming out of this is 41 times minus a, and that has to equal minus 41, therefore a has to equal a 1. Now that we know a is a 1, 2z minus 1 must equal 0, that third bracket, so our third root is a half, where z1, the one given in the question, 5 minus 4i, and z2 from part A, 5 plus 4i. These are our three roots to solve the equation when f of z equals 0. Part C, determine the value of p and the value of q. What's p? Oh, p and q here. P z squared and qz. Now I will have to deal with these brackets here and here to figure out what those are. So if I continue that process down here, we've got z squared minus 5z from the first bracket minus 5z from the second bracket, so that's minus 10z. Then from the first bracket I've got a plus 4iz, from the second one a minus 4iz, so they go away. And then we've got the 41 that we talked about earlier. And now we've got 2z minus a, which we found was a 1, like this. Except I don't need that equals 0 anymore. What this needs to equal is what we were given in the question, which was 2z cubed plus pz squared plus qz minus 41. So the minus 41 matches, the 2z cubed matches. We just need to figure out our z coefficient and our z squared coefficient. So if I do this times this, that gives me a minus z squared, and this times this is minus 20z squared, minus 21z squared, and that has to equal pz squared. Therefore p is equal to minus 21. Now our z term, we need this times this, that gives me 82z, and this times this is plus 10z, that gives me 92z, and that has to equal qz, therefore q is equal to 92. There are no other z terms, no other z squared terms, so these should be our answers. P and q integers, that looks good. When plotted on an Argand diagram, the points representing the roots of the equation f of z equals 0, that's what we found in part B. They form the vertices of a triangle, determine the area of this triangle. Okay, so we're plotting these 3 points on an Argand diagram. Let me do it down here. So one root we found was a half, put that there. And the other two, 5 plus 4i and 5 minus 4i. So our triangle is this triangle here. And obviously from 4 to minus 4, that's 8 units. And from 5 to a half, that's 4.5 units. So the area is equal to half times 8 times 4.5, which is 18 square units. That was fairly straightforward, so long as you had the correct points from part B. I think that's the question finished, so moving on to question 3. The hyperbola h has equation xy equals c squared. Put that here. No doubt going to use that. Where c is a positive constant, the point P, CT, C over T, where T is greater than 0, lies on h. The tangent to h meets P at the x-axis at the point A, and meets the y-axis at point B. Okay, so we've got our hyperbola, something like this, and then it has a tangent at point P, something like this, and that crosses the x-axis at A, the y-axis at B. Determine in terms of C and T the coordinates of these 2 points. So we need the equation for the tangent. To do that, we're going to have to differentiate using the product rule. Differentiate x as a 1, leave the y alone, and then leave the x alone and differentiate the y with respect to x. And the right hand side is a constant, differentiates to 0. So we move the y across and divide by the x. dy by dx is this. At point P, where P is CT, C over T, we can now put those in and the gradient at that point is minus c over t divided by c times t. So it's this, that cancels. Minus 1 over t squared is the gradient of the tangent. So that's m in my line equation, y minus y1 equals mx minus x1. And then we can put it all in. y1 is c over t, m is 1 over t squared, and x1 is ct. So that's our equation, and then we want the coordinates of where this crosses the two axes. So at point A, the y coordinate is 0. And we need to find the x coordinate. So that's minus c over t, 1 over t squared, x minus ct. Oh, I'm missing a minus. That's going to make a big difference. Sorry about that. So the minuses cancel, one of the t's cancel, and we get a ct equals x minus ct. So x is equal to 2ct. Then at b, x is 0. And we need to find the y coordinate. Y minus c over t is equal to minus, don't forget the minus, 0 minus ct. So that's going to multiply with the minus 1 over t squared. The minuses are cancelling, and the t, that will give us a c over t on this side as well. Oh, and the same thing is going to happen. We're doubling up 2c over t. So A, the x coordinate was 2ct, 0, and B, 0, 2c over t. And those are the coordinates of the 2 points where that meets the axes. Given that the area of triangle AOB, where O is the origin, is 90 square units, determine the value of c, giving your answer as a simplified third. So we're using what we just found. The x-coordinate of A gives us this distance here. The y-coordinate of B gives us this distance, and half of those two multiplied together gives us 90. So the area, which is 90, looks like A, area is equal to half of 2ct times 2c over t. That cancels. Oh, so does that, and we get 2c squared is 90, c squared is 45, c is equal to square root of 45, which is 3 root 5 as a simplified third. That is the question finished. Moving on to question 4. Another matrix. Here we've got A. Describe the single geometrical transformation represented by the matrix A. Okay, for questions like this, I always like to apply the matrix, apply the transformation onto the identity matrix, and you know that that does not change the matrix. And then we can consider the identity matrix to be the coordinates of I here, 1, 0, and j here, 0, 1. So if this is I and this is j, then this is I prime and j prime. This is where they are transformed to. And you can see that the I column hasn't changed. I is staying here. So I prime is where I was. But the j vector has transformed. It's now much further up. It's a 3 up here somewhere. And j prime is way up here. So if I hasn't changed and the j has become 3 times bigger, then that is a stretch in the y direction, or parallel to the y-axis. And the scale factor of that stretch is 3. That's part A finished. Part B, the matrix B represents a rotation of 210 degrees anti-clockwise right down the matrix B, giving each element in exact form. Now there's only 1 mark for that, but what I'm going to do would be worth more than 1 mark, because I'm going to do something very similar to what I've done, but backwards. I'm going to consider I and j, and I'll just change colours here to keep it easy to see. And we're rotating 210 degrees. So if I take the I vector and I rotate that 210 degrees, we get 90 here, 180, 210 brings it here, and this little bit is 30 degrees. Then I take the j and I do the same thing, 90, 180, 210, where this little bit here is 30 degrees. Then this is j prime, I prime, the transformed I and j. And to get the matrix A, B, C, D, I need the coordinates of the transformed I and j vectors. Here, the x-coordinate is minus cosine of 30 degrees, and the y-coordinate is minus sine of 30. For the j, the x-coordinate is positive sine 30, and the y-coordinate is negative cosine of 30. So if I put that into my calculator, I get minus root 3 over 2, minus a half, and minus root 3 over 2 again down here. And I think they only give 1 mark there because there is an easier way to do that with the 210 degrees, but I prefer to think of it in the way I've done it there. Either way, you should get this answer here on the screen. Part C, the transformation represented by matrix A followed by, so A is first, followed by means it goes on the left. The transformation represented by B is the transformation C. Find C. So as long as you get this in the correct order, we're doing a matrix multiplication. Minus root 3 over 2 here, applied on A, which was 1, 0, 0, 3. The 1, 0 column isn't going to change. And the 0, 3 column is going to multiply that second column by 3. That'll be 3 over 2 and minus 3 root 3 over 2. Like that. Part D, the hexagon H is transformed onto the hexagon H' by the matrix C. Given that the area of hexagon H is 5 square units, determine the area of H'. So when we're doing this, the area of H' is equal to the determinant of C times by the area of H. We know H is 5, we need the determinant of C, and that is equal to minus root 3 over 2 times minus 3 root 3 over 2. Take away 3 over 2 times minus a half. Why have I got a 3 here? That should be a 2. That gives us positive 9 over 4 plus 3 over 4, which is 12 over 4, which is a 3. 3 times 5. The area is 15 square units. That was the end of that. On to question 5. The quadratic equation given has roots alpha and beta. Without solving the equation, write down the value of alpha plus beta and the value of alpha beta. So we're using the idea that x minus alpha times x minus beta gives us our equation, but because of this 2, I'm not going to put it in the brackets this time like I did with the previous question. I'm going to put it outside like that. Then that can equal 2x squared minus 3x plus 7. So if I just want x minus alpha and x minus beta, then that will give me x squared minus 3 over 2x plus 7 over 2. And then of course expanding the left hand side, x squared minus alpha x minus beta x. So I can write it like that, plus alpha beta like this. And you're not expected to write all of this for 1 mark. I'm just refreshing where this is coming from. So you can see that the alpha plus beta here must equal the minus 3 over 2, but without the minus because the minus is already here. So alpha plus beta must equal 3 over 2, and alpha times beta is equal to 7 over 2. And if that was a minus 7 over 2, then it would be minus because here we've got a plus. So for 1 mark, write down you didn't need that work, but it's always nice to refresh what's going on. Determine the value of alpha squared plus beta squared. Now we know these two, we can manipulate lots of things just with this information. So if I take alpha plus beta, which I know is 3 over 2 from part A, and square it, and then if I expand that on this side, alpha squared plus 2 lots of alpha beta plus beta squared. Now if I rearrange, we can get alpha squared plus beta squared equals the bracket that was on the left minus 2 alpha beta, and we know what both of these are. We know alpha plus beta is 3 over 2, square that, minus 2 lots of alpha beta, 7 over 2. That gives me a 9 over 4 minus 7, which gives me minus 19 over 4 for alpha squared plus beta squared, which seems very strange because you might ask, if you square two numbers and add them together, how can you get a negative out of that? But that is just implying that we've got complex roots, and perhaps there's a reason why we shouldn't solve the equation in the first place. Either way, that's an okay value in this situation, minus 19 over 4 for part B. Part C, find a quadratic equation which has roots of this, giving your answer in the form px squared plus qx plus r, where they are all integers to be determined. Here we're going to be doing a very similar thing to what we did in part A, but backwards. We want to find the value of alpha plus beta and the value of alpha beta in order to work out what the two numbers that go here and here should be. But I'm not going to use alpha beta because we've already got that, and we're using those inside these roots, so let me call that alpha prime, beta prime. So we need to find out what these are, and the roots are these, so let me call this alpha prime, and this is beta prime. So what we're going to do here is we're going to add these two expressions together and manipulate them so that we're using things that we know. Alpha plus beta here, 3 over 2. Alpha beta here, 7 over 2. And alpha squared plus beta squared here, minus 19 over 4. So long as we can make this plus this involve those three things, then we can substitute in the values we've got, and then we'll do the same sort of idea for this times this to get this one. So that's where we're going. Alpha prime, alpha minus 1 over beta squared, was that right? Yes, and then the opposite for beta prime, beta minus 1 over alpha squared. So adding these two together, now we need to manipulate this into those three things that we've got. Already I can see an alpha plus a beta there, that's fine, we'll leave those. But then we've got minus 1 over beta squared plus 1 over alpha squared. That's not something we know from our work so far, but we can manipulate that to add the two fractions together to give us alpha squared plus beta squared, which is what we had, yep, in part A there, divided by alpha squared beta squared, which can be written as this, which if we know, squared. Now these are the three things that we know. We know alpha plus beta from part A. Oh no, that was part B. This is part C. Okay. Alpha plus beta is 3 over 2, so that's here. Minus alpha squared plus beta squared is minus 19 over 4. Divided by alpha beta, which is 7 over 2, squared. And if I put all of that on my calculator, we get 185 over 98. So that's our middle term here. The negative version of that will go there. And now we need to multiply these two expressions to find the other one. Alpha prime, beta minus 1 over alpha squared times alpha minus 1 over beta squared. And that is equal to alpha beta, which we know, minus alpha over alpha squared, so that's 1 over alpha, minus beta times beta squared, or 1 over beta squared, 1 over beta, plus 1 over alpha squared beta squared, which again, we just write that as alpha beta, which we know, squared. Slightly easier with the fractions perhaps this time, although we're doing pretty much the same thing. We've got beta plus alpha over alpha beta, plus 1 over alpha beta squared. Alpha beta, that was 7 over 2. Alpha plus beta, 3 over 2 over 7 over 2, plus 1 over 7 over 2 squared. And that tells me 309 over 98. I'm glad they've both got 98 on the bottom. So when we substitute that into our general equation, we get x squared minus alpha plus beta, or alpha prime plus beta prime. That's 185 over 98x plus the multiplication, 309 over 98. So if we multiply everything by 98 there, we get 98. That should equal 0. X squared minus 185x plus 309 equals 0. Now they're all integers, so p is 98. Q is minus 185, and I think it was R 309. There we go. Question 5 finished. On to question 6. Here we've been given a function, x is greater than 0. For part A, we just need to show that the equation f of x equals 0 has a root in this interval. So to do that, we go ahead and put both in. We want to evaluate at 3.5 and at 2.5. 3.5 minus 4 minus cosine of 5 root 3.5. Put that on my calculator, I get 0.4975 dot dot dot. Take note we're in radians here, not degrees. Then I need the function evaluated at 2.5. Same idea. 2.5, and that gives me the answer minus 1.4483 dot dot dot. Don't forget we need a concluding statement here. Let's put that is greater than 0, that is less than 0. Then you need two key things here. You need to say change of sign from positive to negative or negative to positive. And you need to say that f of x is continuous. Therefore, alpha must be between 2.5 and 3.5. Part B, using linear interpolation once on the interval, find an approximation to alpha 2 decimal places. So linear interpolation is where we are kind of looking at the graph. You don't need the graph to do this, but it's all about the idea that this point here at 3.5 is giving us a positive value, 0.4975 dot dot dot, and here at 2.5 we're getting a negative value, and that's our minus 1.4483, obviously not to scale. And you can make similar triangles here. We've got this triangle here, where we know this and we know this. The middle here is alpha, so this here is 3.5 minus alpha, that's the distance there. And same idea with this triangle here. This distance is alpha minus 2.5, and this distance is this number on the side here. The magnitude of, I should say. So we can set up our equation, and you can do the equation without any of that diagram. You don't need the diagram on the exam. But the key point is that because they're similar triangles, 3.5 minus alpha over alpha minus 2.5 is equal to 0.4975 dot 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 over the magnitude of the other one, so 1.4483 dot dot dot. Now for ease of rearranging this, I'm going to call this number A. I've also stored that under the letter A on my calculator. This one B, and I've stored that under B on my calculator so that I can do this without having to worry about the accuracy getting lost or needing to input it again. So if I rearrange that, I'll have A alpha minus 2.5A. And on the other side, I'll have 3.5B minus B alpha. Rearranging this, on the right hand side, alpha A plus B. On the left, 3.5B plus 2.5A. And then alpha is equal to 3.5b plus 2.5a all over a plus b. I don't know why that's lagging. And putting all of that on my calculator gives me 3.24432 dot dot dot. We are working to 2 decimal places, so that 3.24. So that's our answer to part B. Now that, they've got a slightly funny thing here. This is I. Now we're on part 2. Part A of part 2 is just to differentiate this function. So I'll take that and we'll immediately rewrite it because I don't like having the x in the denominator. So let's have x minus 2 over 2 there. Remember, don't take the 2 up as well. It's just the x with the power. If you turn that into minus 2x to the minus 2, you would get the wrong answer. Now differentiating this, 2x over 10. Here the minus 2 comes down, that becomes a plus 2x to the minus 3 over 2, plus 1, and then a 0 for the minus 11. Simplifying that, we get x over 5 plus 1 over x cubed, putting it back how it was, and that is our derivative. Part B, the equation g of x equals 0 has a root beta in the interval 6 to 7, so we're using x naught equals 6 as the first approximation and applying Newton-Raphson. You're not expected to remember the Newton-Raphson formula that's given in the formula booklet. So we've got x naught is equal to 6. And then here in the FP1 section of the booklet is the Newton-Raphson formula. So that's there on the side. The only difference, of course, is we're using g here, not f. But good enough. x1 is equal to x naught minus g of x naught. Let me change that into a 6 already. Over g prime 6. G of 6, if I put all that on my calculator with a 6, is minus 509 over 360. And g prime of 6, if I put that all on my calculator, that's 2381 over 1080. So this becomes 6 minus 509 over 360 all over 2381 over 1080. And that comes out as 6.64132 ... How many decimal places? 3. And we only need to find a second given the first, so we're only doing this one time. 3 decimal places, and we've finished the question. There we go. Moving on to question number 7. Question number 7 at first glance looking very similar to the hyperbola question earlier. We've got an equation here of y squared equals 4 over 3x. We've been given a point P where t is not equal to 0, and we need to use calculus to show that the normal to C at P has equation given here. So similar but not quite the same. Differentiating this, we get 2y times by dy by dx. On this side, 4 over 3. So dy by dx is equal to 2 over 3y. Now at point P, dy by dx, we substitute in the y, and the y is 2/3 of t. So that's times by 2t over 3, so all of these cancel out, and we get 1 over t. Now I'm going to call that m1, that's the tangential gradient, and we want the normal. So m1, m2 must equal minus 1, so m2 is equal to minus t. Putting that into our standard line equation of whichever format you want to use, I'm going to use this one, together with the points, and the gradient here is minus t, second one we're using. Y doesn't change, x doesn't change, but then we need y1, x1, 2/3 t for y1, and 1/3 t squared for x, oh, I've got x2 there, x1, multiplying out the bracket, minus tx plus 1/3 t cubed, minus 2t over 3 and a y. Let's bring the x and the y together. Tx plus y is equal to 1/3 t cubed plus 2/3 of t. Is that what we're looking for? Very close. So multiplying across by the 3, we get 3tx plus 3y equals t cubed plus 2t, which now matches what they require. Part B. The normal to C at the point where t equals 9 meets C again at the point Q. So P is one of the meeting points and Q is the other. Determine the exact coordinates of Q. We're going to do this by putting t equals 9 into the equation that we found, which was given to us in part A. So it's worth noting that you can do part B here without having done part A. We're going to put t equals 9 in here, and then we're going to rearrange and combine this and this as simultaneous equations and solve. One solution should give us this point with t equals 9, and the other solution is the point Q that we want. We're looking for exact coordinates, so it might be irrational or even a third. So putting that in, part B here, t equals 9. At the top of the screen there, 27x plus 3y equals 9 cubed plus 2 times 9. My calculator tells me that's 747. Like that. And then we need to combine that with the original equation given in the question, which was 4/3 of x. To do this, I'm going to manipulate to make x the subject by doing 747 minus 3y divided by 27. And then I can just drop that in here with the 4/3. My calculator tells me that's 83 over 3 minus y over 9. Multiplying that out is 332 over 9 minus 4y over 27. And that's y squared. Get rid of all those pesky fractions. 27y squared is 996 minus 4y. And then we're solving to find y. Solving this, minus b plus or minus the square root of b squared, minus 4 times a times c, which hopefully gives us a nice number, because the coordinates of p looked like they were going to be fairly nice. It does. That big square root simplifies to 328. So the positive root is a 6. And when you put the negative in there, you get minus 166 over 27. Putting that back into the expression for x gives 27. And the not very nice 6889 over 243. Okay, I'm going to double check coordinates of p match one of those. So if I put this t equals 9 in here, we get 27 and 6, which is good. So that matches here. P 27, 6, therefore Q is the other one. 6889 over 243 and minus 166 over 27. That is the end of part B. They weren't thirds in the end, but irrational. So let's move straight on to question number 8. Part 8, use the standard results for summations to show that for all positive integers n, this big thing is true. Okay, first of all, let's remember that we can split these into individual bits. First of all, expanding this out, we get 2r cubed minus 3r squared minus r, and then we can split this into 2 times the sum of r cubed minus 3 times sum of r squared minus the sum of r. Each of these is 1 to n. And for r squared and r cubed, these are given in the formula booklet. Same page as before, here they are. Note that you don't have the sum of r given to you. That's one that you should either know or be able to quickly work out on the side of the paper. If you remember this, skip over. I'm going to quickly prove it. We've got 1 plus 2 plus 3 dot 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 plus n minus 1 plus n. And then the sum, if you reverse that, you've still got all the same terms. And then you add the two together, and you get n lots of n plus 1. But that's 2 lots of the sum. So you have n lots of n plus 1, and then you have to divide it by the 2. So that's the sum of r from 1 to n, and then taking the other two from the formula booklet here. So I've put each of the 3 there, so we've got 2 lots of this one for r cubed, minus 3 lots of this one for r squared, and then minus this one on the end for the r. Now we need to make that look like this here. I'll just put them all together. Half n squared n plus 1 squared minus, there's another half n plus 1, 2n plus 1 minus a half n plus 1, and if we factorize out the half n, yep, nope, half n and an n plus 1, half n plus 1 is in each of these, so here on the first one we get left with n plus 1. For the second one we get left with a 2n plus 1, and the third one just leaves us with a minus 1. Focusing on that bracket just for a second, we get n squared plus n minus 2n minus 1 minus 1, n squared minus n minus 2, which factorizes to n minus 2, n plus 1. So that's this bracket here. So we get a half n plus 1, and then these two brackets, n minus 2 and another n plus 1. So we just bring those together, n plus 1 squared, n minus 2, and hopefully that is what it said, yes. Part B. Hence, show that for all positive integers n, this big thing here is true. Looking at a bit more detail, this, double check that matches. It does. But then we're not going from 1 to n, we're going from n to 2n. And then when we're finished and we get it to look like this, all of these 4 should be integers. So we're using what we just found without any changes, but we are going from n to 2n, and that is the same as going from 1 to 2n minus 1 to 1 less than n, i.e. n minus 1, because we still want the n to be included in the sum. So I need to put 2n in the expression immediately above this, and n minus 1 into that expression as well. So that's going to be a half of n, which is now 2n, times 2n plus 1 squared, times 2n minus 2, minus the whole thing again with n minus 1, so that's n minus 1 here, then n plus 1, where n is actually n minus 1, that becomes an n squared, and then n minus 1 minus 2, n minus 3. Hope that was clear. Now I need to tidy all of this up and make it look like the thing that they had at the top, which was 4 brackets, 3 brackets and a half n. So let's get rid of that 2 there, and at the same time I'm going to factorize a 2 out of this bracket here. So there will be a 2 there, then an n, 2n plus 1 squared, and then here this will be n minus 1. This is still half, but there is an n minus 1 in both terms now, and there's an n in both terms, that's good. So I'm going to force out a half n minus 1. So from that first term, forcing out a half gives me 4 now, but the n is not there, the n minus 1 is not there, we just get 2n plus 1 squared. And from the second term, I'm missing a bracket, from the second term we've taken out a half n minus 1, but there's still a minus, there's still another n, and there's an n minus 3. Then like before, I'll just focus in on this square bracket here. We get 4 lots of this thing squared is 4n squared plus 4n plus 1 minus n squared plus 3n. Then 4 times that, 16n squared plus 16n plus 4 minus n squared plus 3n gives us 15n squared plus 19n plus 4. And because we know we're looking for 2 more brackets with integer coefficients, that I guess will factorize. So I think we're looking 19 splits into a 15 and a 4, so let's keep that like that for now and put the 4 over here. Will that work? Get the 1 there. Yes, I think that will work. So that big expression, this is still there, and then the square brackets becomes 15n plus 4, n plus 1. And I won't bother writing a equals b equals etc. But that works. We've got a half n minus 1 and then 2 other brackets. Yes. Moving on to question number 9. Given this expression where lambda is a real constant, determine z, giving your answer in the form x plus y I, where x and y are real, and in terms of lambda. So we've got 3z minus 1 over 2. is equal to lambda plus 5I over lambda minus 4I. To split this into real and imaginary parts, we need the imaginary part out of the denominator. To do that, we're going to multiply by the sort of the opposite, if you will, like this. Say the opposite, I should give it its proper name and say the conjugate of the denominator. In the numerator, that gives us lambda squared plus 9 lambda I plus, no, minus 20 because of the I squared. In the denominator, we get lambda squared, and then the whole point of this is that the minus 4 lambda I and the plus 4 lambda I cancel out, and we get minus 16I squared, which is plus 16. On the left, we've got the same as we had. Then we're going to bring the 2 across. 2 lambda squared plus 18 lambda I minus 40, lambda plus 16. And then when we add the 1, of course, we're going to have to change that into a fraction in order to actually add them together. So when we do plus 1 here, we're going to change that to match the denominator. That will be a 3z, and then hopefully we'll get multiples of 3 here. I can see the lambda will be. And then, yeah, we still got 18 and lambda I minus 24. Great. And then lambda squared plus 16. Divide everything by 3. Lambda squared plus 6 lambda I minus 8 is over lambda squared plus 16. That was a lot of work to get to the point where we can split this into real and imaginary parts. So our real part is just lambda squared minus 8, and that's got the denominator. And then when you split your fraction, this part obviously has the same denominator, and that is the I term. So this is z, where this bit here is your x, and this bit here is your y, in the x plus yi form here. That was part A. Given also that the argument of z is equal to pi by 4, find the possible values of lambda. Now it's easy to immediately think that inverse tan y over x is equal to the argument of z. And if I write theta and consider the diagram, that's fine, that's correct. But don't do that without considering the diagram, because that's not exactly the same as the argument of z. It is the same in the first and fourth quadrants only. So if it's here, then this theta is equal to the argument. If it's down here, this theta is equal to the argument, because it will become a negative. But if it's over here, that's not true. The theta will be this one, and the argument, or the principal argument, is this one here. Same in the third quadrant. Theta, you'll be measuring this one, whereas the argument, the principal argument, is this one, a negative value. The reason that matters is because you might end up getting more answers than you should if, for example, you say here that the tan of pi by 4 is equal to 1. That's going to give you this one here, which is great. That's probably the one that we're going to want. That's definitely the one that we want, because pi by 4 here, that's correct, to this angle here. But it will also give you this one, because this angle here is also pi by 4. But that's not the argument. So we'll have to be very careful when we get to the end here, although it does pluralize values here. But my point here is keep in mind the diagram. Don't just rely on this. We are of course going to start with this though, because we do know that the tan of pi by 4 is 1, and we know what y and x are to put into this. So coming down here, part B, tan of pi by 4 is equal to y over x, initially, checking the diagram later, and that is 6 lambda over lambda squared plus 16 over lambda squared minus 8 over lambda squared plus 16. The denominators cancel, and that gives us 6 lambda over lambda squared minus 8. And on the left of all of that, tan pi by 4 is equal to 1. So 1 is equal to 6 lambda over lambda squared minus 8. Multiply that across, lambda squared minus 8 is equal to 6 lambda. And then, of course, we're solving a quadratic equation, which is where having 2 roots is going to come out of, probably. We get 6 plus or minus the square root of 36 minus 4 times a times minus 8, all divided by 2 times 1, not 21, 2 times 1, and that is equal to 6 plus or minus root 68 over 2, and that simplifies on my calculator to 3 plus or minus root 17. Now, as heavily emphasized before, back to the diagram, if we want the argument to be pi by 4, then this is the only quadrant that can be in, which means both the y and the x must be positive values. They cannot both be negative, which would still give you the 1 if you put that into this equation here, because the two negatives would cancel. So if at this point you ended up with 2 answers, you would lose that last mark in this question, but you would not be alone. I'm pretty sure lots of people would do that. It'll come about if you don't consider where it is on the diagram. So with that in mind, we need to double check. There might still be 2 answers, but we need to double check y and x will both be positive if we put both of these numbers 3 plus and minus root 17. 3 plus root 17 is obviously positive. 3 minus root 17 is negative. So coming back up here, so the x is a little more complicated because we square lambda both times. We would have to subtract the 8 and c, but I can see without doing any calculation that y will be negative if lambda is negative because of this numerator here, and it will only be positive if lambda is positive. So regardless of the x, it doesn't really matter because they both need to be positive, and I can see that will only happen with y if lambda is positive. So we need to reject one of these. Y must be positive, therefore lambda is equal to 3 plus root 17. An easy to lose final mark there. Don't worry if you lost that mark. Just try to remember to look at the diagram for future questions that relate to the argument of z. Moving on to question number 10. Prove by induction that for n is any positive integer, this matrix statement is true. So with our induction, we've got 4 steps. The first is the basis step, and that is to try n equals 1 and show it works. 5 minus 1 for 1 to the 1 is obviously just this. That's the left-hand side. Right-hand side, put it in as well. We get 3 to the 0. 2 plus 3 minus a 1, 4 times a 1, and 3 minus a 2, that gives us a 1 in front. 5 minus 1 for 1, which is the same as the left-hand side. Therefore it is true when n equals 1. Great, that's our first step. The second step is the assumption. We are going to assume it's true for n equals k, and that gives us this statement to use in our inductive step. 3 to the k minus 1, 2k plus 3 minus k, 4k, and 3 minus 2k. So I can use that in the induction, which is the next step. Induction, and this is try n equals k plus 1 and show that it works if we use the assumption statement. So here I'm going to start with the left-hand side matrix with k plus 1 and make it look like the right-hand side with a k plus 1. To do that, we're going to separate the index powers here. We're going to have 5 minus 1 for 1 to the k and 5 minus 1 for 1. And because that's the same, it doesn't matter if that's on the right or the left. I'm going to put it on the right so that the 3 to the power is in front here on the left. So that's a k minus 1 using this statement here to transform this matrix into this one. So this is followed by the matrix 2k plus 3 minus k, 4k, 3 minus 2k. If our assumption is true, we can replace that k matrix with this, and then we still have 5 minus 1 4 1 on the right. But now we can do this matrix multiplication because there's no power of k involved. So in the first element we get 5 lots of 2k plus 3, that's 10k plus 15, plus 4 lots of minus k. Second element, minus 1 of this, that's minus 2k minus 3, plus 1 of the minus k. Next element is 5 lots of 4k, plus 4 lots of 3, so that's 12, minus 4 lots of 2k, 8k, and then minus 1 lot of 4k, plus 1 lot of 3 minus 2k. Tidying this up a little bit, we get 6k plus 15, minus 3k minus 3, 12k plus 12, and minus 6k plus 3. Now what we need is for this to look like what we had here, but with a k plus 1 instead of a k. So all the manipulation that follows is aimed at doing that. So we need a 3 out the front, because if I put a k plus 1, this should become a k, not a k minus 1. So to do that, I'm going to take a 3 out of all of this. That leaves us with a 2k plus 5 here, minus 3k plus 1 here, 3 lots of 4k plus 4 here, 3 lots of minus 2k plus 1 here. Take that 3 out and we get a 3k here. And that doesn't look like a k plus 1 obviously, but that's a k plus 1 minus 1, so that is correct. And inside we've got 2k plus 5 minus k plus 1, which is correct, I think, to the minus k here. That one's okay, that one's correct now, so is this one. Here we've got 4 lots of k plus 1, so this one is also correct now for a k plus 1. Then we want minus 2k plus 1 here. So that first element, 2k plus 5, needs to look like 2k plus 1 plus 3. That kind of already does, we can just rewrite that. 2k plus 1 gives me a 2k plus 2, and then I have to add 3 to make it true, so that's correct now as well. That's that one. And then we've got 3 minus 2k plus 1. So minus 2 lots of k plus 1 would give me a minus 2k, that's okay. And then a minus 2, but there's actually a plus 1 there, so we need a 3. So yes, that works out just right. 4k plus 1. And this is 3, if you want to write it like this, k plus 1 minus 1. And that is the right-hand side as we needed it. And still on the left here is 5 minus 1 for 1 to the k plus 1. So it is true for n equals k plus 1 if it's true for n equals k, because we used that assumption step at the top right near the beginning. And we've shown it's true for n equals 1, therefore true for all positive integers. And yes, you need that concluding statement there for the final mark in the exam. So that is a big part A, but that's part A finished, 5 marks. Oh, part A, part I. Part II, prove by induction that for n is any positive integer, this is divisible by 7. Okay, same idea, proof by induction, but completely different question. All of this first part is altogether separate. So I'll take that function, put it down here. And what we're trying to show is that you can divide this by 7. So we do the same sort of thing. We've got the basis step first. N equals 1, show it's true. 8 to the 2n plus 1 is a 3. 6 2n minus 1, that's a 1. That equals 518, which is the same as 74 times 7. Therefore, divisible by 7. Therefore, true for n equals 1. Then our assumption, true for n equals k. So what I'm going to write here is 8 to the 2k plus 1 plus 6 to the 2k minus 1 can be written as 7 times p, where p is an integer. And that shows that the number is divisible. Like I've got here, 7 times 74. 74 is an integer, therefore the divide by 7 is true. Third step, the induction. We're going to try n is equal to k plus 1, and hopefully we can prove something similar, that if you do 7 times an integer, you can get this expression. To do this, I'm going to do my standard approach when I try to prove things are divisible. I'm going to take f of k plus 1, and of course that's equal to itself, and then I'm going to add f of k and subtract f of k, and you can see that that statement is true, but when I put in all of the expressions that we've got, this will help me have enough terms to manipulate to show that it is true. So if we get k plus 1, that's 8 to the 2 k plus 1 plus 1, plus 6 to the 2 k plus 1 minus 1, and then plus these other terms, 8 to the 2k plus 1, plus 6 to the 2k minus 1, minus 8 to the 2k plus 1, minus 6 to the 2k minus 1. And remember, we've assumed that these two together are divisible by 7, and then I can use these other two as part of my manipulation to show that the rest of it is divisible by 7, or the other way around, I can show these two are divisible by 7 and add these two for my manipulation. So either way, we've got some work we can do here with these terms. First of all, I'm going to expand those brackets, 2k plus 3 plus 6 to the 2k plus 2 minus 1, that's a 1. And then plus these other terms, I won't bother writing those. They're not useful just yet because I want to manipulate these powers to match so that I can actually add or subtract them. So we want a plus 1 here. That means I need 8 squared as a multiplier. And I want a minus 1 here, so that means pulling out 2 lots of 6, so that's 6 squared as well. And then those other terms as well. That gives me 64 lots of 8 2k plus 1, plus 36 lots of 6 2k minus 1, plus what am I going to do? 63 and 35 will divide by 7, so I'm going to subtract, so that's useful. I'm going to have the 7p there for the addition ones like I've put here, and minus 1 lot of 8 to the 2k plus 1, minus 1 lot of 6 to the 2k minus 1. Now I can actually put those together. So we've got 63 lots of 8 2k plus 1 and 35 lots of 6 2k minus 1 plus 7p, and we can take out a factor of 7. 9 lots of 8 2k plus 1 plus 5 lots of 6 2k minus 1 plus 7p. And then I can write that as 7q plus 7p. And then we know that k is an integer. That wasn't an assumption, that's part of our process. K is an integer. Therefore, q is an integer. And if n equals k is true, then p is also an integer. That was our assumption. And if that's true, then this is true because you can see 7q plus 7p is obviously divisible by 7. Write it like that. Therefore, n equals k plus 1 is also true. And of course we've shown it's true for n equals 1. Therefore, true for all positive integers. Oh, my handwriting's getting terrible. But still legible, which is the important thing in an exam. And I think we have come to the end of the exam. So those were my conclusions for that bit, and we finished. Yes. Okay, I hope that was helpful for you.